Continuing on with class 4, here's a coordinate transformation example that I came up with. I think there's some other videos from past semesters that I have included in Blackboard that will help you. The more examples that you work through, the better you're going to be able to get this, because it doesn't make the coordinate transformation doesn't make a lot of sense until you start using it regularly. So let's see here. Okay, so we have this. We have this link right here, right? And this link, it has this orientation where theta is right there, and on the end of it, maybe it's got some force P, and that force is a vector, right? And we know that vector is got magnitude of 4 in the I direction and 2 in the j direction, right? So we know its coordinates, we know its components, excuse me. But we also know the orientation of this is equal to 75 degrees. So it's going to, what would help us is to figure out how much of this force is going to cause, let's say, and that should be upwards. It almost looks like it's on line with the thing. That should be upwards. We would like to know that and that instead, right? We want to break this thing down into coordinates. Let me draw the arrows maybe a little bit better there. We want instead to have arrows that show us what's going on in this new coordinate system that we're calling E1 and E2, right? Which in essence are going to be tangent right here, but also this is normal, right? Because it's going towards the center of the piece. What that'll give us in terms of mechanics and materials, right? It'll give us the tension or compression that's in the member, and then this will give us what the torque is, right? So there's a meaningful thing right there. Now I know this can actually be done with cross products in that particular case onto the thing, but here instead we just want to do a transformation. So we just want to know what is this vector, but instead of being in I and j, we want it to be in E1 and E2, something that somebody has created, right? So it's good to make a drawing and to be careful with the drawing and maybe even use a straight edge. So I will use the so impressive Westcott B55 see-through. Did they write the see-through on this one? No, they didn't. Some of them have say see-through on them. I wonder if I got a different. Yeah, I don't know. Anyway, I like it because it's tenths, and it has tenths of inches, and it has millimeters, centimeters on it, so you can break things down and scale things easily. Okay, so I'm going to trust that this orientation is correct, right there. So here is our other vector, and here is our other vector, right? Unit vector. So here's I, and here's j, and here's E1 with a caret on top, and E2. And one good thing to do if we're messing around with this is to draw lightly, extend the lines down. Extend these lines. That will help us. Also help us kind of decide where this angle is taking place now. So this angle is this right there. If we want to use theta, we don't have to use theta. We could actually, we want to invent our own angle and do that one right in there, and then that would be useful to us in some respect. That would be this angle right there. We could use the complementary angle, but let's use this right here. So if that is theta, then this is theta, right? Because they're opposite from each other right there, right? And we could also say that this was theta and this was theta, but I don't want to overcomplicate it. So let me do my array here. All right. And I'm going to pick I and j on the top, and E1 and E2 right there. Now, so we've already covered how to construct this in the previous one, but it's good to have practice here. Take a look at E1 in the I direction, and you'll see that it's going to be, remember, this is the angle right there. First off, this guy is in the negative I direction, right? So he's going to be negative. And then if theta is the angle, it's going to be the cosine, right? So if this is we're taking this is the magnitude that we will be using. So we're going to multiply this magnitude by cosine or sine to be able to get the I direction. And in this case, it's going to be adjacent, right? You could even make a little line right there. We'll say that's not that line, but this line right there. That's the one that we have there. So that's cosine of theta. And now we can get E1 in the j direction, and we'll see that that's going to be negative, right? E1's pointing downwards with respect to j, and it's opposite from the angle. So and it's negative, right? So it's negative sine of theta. Now take the E2, right? And maybe it'll help us to put the theta right there, right? And so in the I direction, we can actually just get, at this point, kind of guess a little bit, but we'll see in a second where maybe guessing would have been right. We note that this is going to be in the negative x direction, right? E2 is going that way, opposite, and it's opposite from the angle, right? So it's going to be like, it's like that guy right there, opposite there. So since it's negative and then sine theta, and then we go to E2 in the j direction, and we can see that it's going to be positive j, and it's going to be the cosine, cosine, right? Because it's the adjacent side of this right there, and j. So we have that same pattern that we had before, right? Where we have opposites from each other, and then one of them is the opposite sign from the rest of them, right? So now it's really about using this, right? So we're starting off with I and j, and we want to get it in terms of E1 and E2. So if we take I and multiply by this and this with the E1 and E2, and then we take j and multiply it by this one and this one for the j. So that looks like this, right? It's still the same vector, it's just going to be in terms of something else. So I'm going to do this slowly. I'm going to do when you get used to this, you could do that. You could skip a step here, but we'll do this step. We'll take that 4, and we're going to multiply it by negative cosine of theta E1 and then we're going to have it multiplied by negative sine. So it's also going to be negative sine of theta E2, right? I'm just putting brackets on there to make sure that we noticed that's what we did before. We distributed it over E1 and E2. Then we do the same thing for 2 here in the j. So we go down in columns, and we take 2 and multiply it by negative sine of theta E1 plus positive cosine of theta E2. We can collect the E1 and collect the E2. So we have 4, and maybe I'll put the negatives inside by the 4s right here. So we got inside the values, right? I'm taking that negative out and going cosine of theta. I'm going to do both for E1s, so I'm going to leave that here. I'm going to go grab this one. So we say plus negative 2 times sine of theta times E1 plus 4, let's make it negative, sine of theta plus 2 times cosine, and it's positive. So we've just transformed the things, right? So that's how we use the array. But anyway, if we plug in 75 degrees for here and there and here and there, right? I'm not going to rewrite the thing out. And we plug it into our calculator, we get P is equal to negative 2.967 E1 plus 3.346 E2. And they didn't give us a units, but it'd be good to put a units in there. But this kind of makes sense, right? I'm going to give a little sanity check and look back at the original part of the problem and see, well, E1's pointing downwards, but we know that this guy's going. It would have a component in the negative E1 direction. Makes sense. And then this guy is in the positive E2, which is coming out there. This would be the force that would act on this thing axially, and this is the one that would act on it to cause some torsion onto the piece. But this is a useful thing to do, and I'll try to incorporate it into some other problems. So thank you.